Okay, so we're just going to pick up, continuing in on these problems. We start by, we're just graphing the equation, and we take a look at the roots. We see here, this one is going to be a little bit different because um, this is a degree 3, which means that there is 3 roots. But when we look at the graph, we only see one real root. If we go back to the rational zero theorem, then that states that the leading coefficient of the first term, that x cubed, that's 1, and the constant is the 5 back over here, and so the possibilities of all the rational roots are plus or minus the factors of the constant, which is 1 and 5, and the factors of the leading coefficient is 1. So that means that we have plus or minus 1 and 5, which means that we have four possibilities. The negative 5, negative 1, 1, and 5. We only see one. We only see one root, x-intercept, or solution. But we need 3. We look for repeated. It's possible that there is a repeated root, but there is another possibility, which are the complex roots. And so these are complex numbers of the form, a plus bi, where a is the real component and the bi is the imaginary component. And this comes, boy, if I can spell, imaginary. Here we go, imaginary. There we go. That's better. Where a and b are real values, real numbers, and the number I is the square root of negative 1. So the thing about these kind of roots, imaginary, they always come in pairs. They always come in pairs. So a plus bi and a minus bi. If they don't come in some kind of a pairing, which this is called the complex conjugate, then you're going to see i's all throughout the polynomial. And when we look at this original polynomial, I don't see imaginary terms, but but I only see the one real root. So let me go back to the graph, and if you look right here at this particular vertex, you see that the graph changes, but something has to control that change. If you look over on the left side, you see that the graph is going up, but for some reason it turns back down and then goes back up again. Something has to be controlling that change, and that change is controlled by the imaginary roots, which since they are not real, are not going to intersect the x-axis. And so how do we deal with those? Well, we're going to go back. We're going to start with the similar process as to what's going on, as to what we have done before, which is we're going to look at the case of the root of x minus 5. So with that, before we get into that synthetic division, because this is just a repetition of the same kind of problem that we've done before, I do want to mention the possibilities of roots. I've said before, this is degree such and such polynomial, which means that we have at least this many, or at most this many. I've used some kind of term describing the real roots, and so this is why. This is a degree 3 polynomial, which means that we have at most 3 real roots. But we are guaranteed to have 3 complex roots, or again, solutions. So if I said real roots, and I also looked at imaginary roots, the thing with this is that the imaginary roots must always come in pairs. And so there's the possibility of 0, but then there's also the possibility of 2. The next possibility potentially would be 4, but this is degree 3, so we can't exceed that, which means that there is either 3 or 1 real root, which we saw in the graph. And in the next problem, we can take a look at that a little bit more before we go to the graph. So we have this root x equals 5. When we synthetically divide, if we get remainder of 0, then that means that x plus 5 is a factor. And so now we just kind of move into this process. This is a negative 5 that goes in the box. 1, 5, 1, 5. Bring down your first term. 1 times negative 5 is a negative 5, plus 5 is 0, times 0, or sorry, times negative 5 is 0, plus 1 is 1, times negative 5 is negative 5, and we get 0. This is x squared plus 0x plus 1. And so that means, so we are correct in that x plus 5 is a factor, and x squared plus 1 is the other factor. If I graph these two, the product of these two factors, I should get, that was 5, an overlapping graph. So this is x squared plus 1. The graphs overlap as we had predicted. And I want to take a look at this graph, the x squared plus 1, and you see that this graph never crosses the x-axis, which means that it has complex roots. But how do you find complex roots? The same way, you find them the same way that you always did, which is in the quadratic formula. If x squared plus 0x plus 1 equals 0, that means a, which is the coefficient in front of the x squared, is 1, b is 0, and c is 1. And so let me get that out of the way for the moment. So we fill in the quadratic formula, the opposite of b. X is equal to the opposite of b, plus or minus square root minus 4ac, all divided by 2a. Plug in our values for a, b, and c. So this is the opposite of 0, plus or minus square root of 0 squared, minus 4 times 1 times 1. Because this was a times 4 times a times c, all divided by 2a. Now simplify. Opposite of 0 is just 0, plus or minus 0 squared is 0. 4 times 1 times 1 is just 4. And 2a is, or sorry, 2 times 1 is just 2. Simplify just a touch more, you get 0 plus or minus 0 minus 4 is a negative 4 divided by 2. And I'm going to work this little part as kind of a side note. So what I'm writing in red is how I'm going to make the jump to the next step, which is negative 4 is the same as negative 1 times 4. And we've looked at this technique previously. The product, the square root of a product is the same as the product of the square roots. So the square root of negative 1 times 4 is the same as the square root of -1 times the square root of 4. And the square root of -1 is I. Square root of 4 is 2. So I times 2 we frequently just write as 2I. So now this value for x is going to be 0 plus or minus 2I all divided by 2, which is now the same as 0 divided by 2 plus or minus 2I divided by 2. And so you end up with this 0 plus or minus I. 0 divided by 2 is 0, and then 2 divided by 2 is 1, times I is just I. And finally, we have that the roots, the remaining two roots are plus or minus I. If I write these out as two separate roots, so this is I and negative I, then I can write them out as factors. Remember, I is just a number. So for the one on the left, I'm going to subtract I from both sides. So I get x minus I. And that is one of my factors. And then I add I to both sides over here on the right hand, on the right equation, and I get x plus I equals 0. And so those are my other two factors. We always write our complex factors at the end of the polynomial. And so this is x plus 5 times x minus I times x plus I. And just out of curiosity, will Desmos recognize this? No. Okay, so it's wanting to treat I as a variable. So when it comes to graphing, and when it comes to graphing these things, that's as far as you can take this graph. You're not going to be able to take it any further. But we can still use that information to help guide us to what is the final answer. So this is the last one, I believe. Yes, it is. It is the largest one. Feel free to pause this video and you try this one for yourself. I am going to go ahead and move on, starting with that same technique. And before I do that, so, what's the degree? What is the degree of this polynomial? It is degree 6, which means at most, how many real roots are there? Which is 6. There's at most 6. But what I want is, now what are the possibilities for the real roots as opposed to the possibilities of the imaginary? I'm not doing well on my spelling this afternoon. I apologize. And the imaginary always come in pairs, and the first pair that really we want to look at is 0. If there's 0 imaginary roots, that means that there's 6 real. If there's 2 imaginary roots, then that means that there's 4 real. And if there is 4 imaginary roots, that means that there's 2 real. And then finally, if there's 0 real roots, that means they all have to be imaginary. If you notice that the pairing of these numbers always has to add up, to be the degree. So, before I go to the graph, I check, do I see 6, 4, 2, or no intersections with the x-axis? And so when I graph this, I look and I see at first what appears to be 3. But if I zoom in, I see that this is touching the graph. That's a reflection. That's multiplicity 2, which means that I have the root of 2 twice. So I have 1, 2, 3, and 4. And so that lines up with everything that we have. So I see positive and negative 1, and then I see a positive 2 twice. Like one of the others, I'm actually going to go a little bit further in my division before I actually start verifying things on the graph, because we were saying that x is negative 1, x is 1, x is 2, and x is 2 are indeed roots. So I'm going to set up a synthetic division. I like to use the largest magnitude number. Regardless of if it's positive or negative, which is overall the largest number. And in this case, both times it's going to be 2. So let me start with those first. So there is 2. It's 1 to the 6th, 2 to the 5th, negative 8 to the 4th, negative 30x cubed, positive 59x squared, 28x, and minus 52. And hopefully we'll get a remainder of 0. Bring down the 1. Times 2 is 2. That is 4. Times 4 is 8. Minus 8 is 0. 0 times 2 is 0. Minus 30 is a negative 30. Times 2 is a negative 60. Plus 59 is negative 1. Times 2 is a negative 2. Plus 28 is a negative 26. And times negative 26 is positive 52. And there is my factor of 0. If we were to use the rational zero theorem now, we would have to find all the factors of 26, which actually are not that many. It would be 1, 2, 13, and 26. So it's still fairly easy to work with. Overall, not too bad. But because we use the graph, I can kind of skirt using that rational zero theorem right now. And I want to go ahead and try, since we saw that reflection at root positive 2, I want to try the second root again. And so this is going to be root 2. And we bring down the 1. Multiply by 2, that's 2. Make sure that I've done this right. 4 plus 2 is 6. Times 2 is 12. Plus 0 is 12. Times 2 is 24. Minus 30 is a negative 6. Times 2 is negative 12. Minus 1 is negative 13. And then times 2 is... Oh, I see what I did wrong. Because negative 13 times 2 is a negative 26, but then up here, up above, the 28 minus 2 is plus 26, which times 2 is plus 52. So that was my mistake. So now I get positive 26 minus 26 is 0, so the number 2 is a root, and the value of x minus 2 will be a factor. But we'll get to that. We'll get to that in a minute. So now I'm working here. This that represents, so the 13 is the constant. This is degree 4, and so this would actually represent the polynomial 1x to the 4th plus 6x cubed plus 12x squared minus 6x minus 13. But I'm not over concerning myself with it, because we still had the other two roots of plus or minus negative 1, and whichever one that you would want to work with, it doesn't really matter. I'm going to use the 1 because me personally would rather deal with the negatives in the smallest uh, would deal with the negatives with like the smallest problem possible. I'm more comfortable with positives. So we're just continuing the synthetic process. Bring down the 1. 1 times 1 is 1, plus 6 is 7, times 1 is 7, plus 12 is 19, times 1 is 19, minus 6 is 13, times 1 is 13, minus 13 is 0. So 1 is a root, making x minus 1 a factor. The last one that we saw was a negative 1. Rational zero theorem. So the constant, the leading coefficient, 13 is prime. So you only have 1 and 13 as possibilities in the top. And 1 is just 1. It's not actually prime. And so the possible real solutions that would be left are plus or minus 1 and plus or minus 13. We've been narrowing this down and making things a lot easier as we've been going along. So if I go to the 1 times negative 1 is a negative 1. Plus 7 is 6 times negative 1 is a negative 6. Let's see here, plus 19 is a positive 13. And then times negative 1 is negative 13. And when you add 13, you get 0. So at this point, we have seen roots 2, 2, positive 1, and negative 1. And if I subtract 2 to both sides, that gives me 2 factors of x minus 2 because we had 2 roots of positive 2. If I subtract 1 from both sides, I get x minus 1 as another factor. And then when I add 1 to both sides, I get x plus 1. And so these 4 factors are part of what make up this graph. So for the first time, in this particular problem, I'm going to graph now to verify. Most likely because I kept getting this, the remainder of 0, then this graph, this graph will line up and be correct. But there is that possibility of somehow I made mistakes that didn't show up. So the danger in this is if I happen to run into one of those rare cases where I made mistakes but was able to still work the problem, I don't know in which of the 4 steps I messed up. But so far, things are looking pretty good because when I go back to the graph, I see a reflection at 2. I see intersections at 1 and negative 1. So the last part is what goes here to make this a degree 6. We have 1, 6, and 13 left over. So this is 1x squared plus 6x plus 13. And when I graph x squared, 6x plus 13, everything lines up perfectly. So I've gotten 4 out of 6 things done. When I graph that x squared plus 6 plus 13, I see that it does not intersect the x-axis. So if I wanted to carry this further, then I would have to use the quadratic formula. So I'm sorry I kind of ran out of room a little bit there, but let me see if it'll let me move. Yeah, it'll let me move. That way I can write this a little bit bigger. So I'm okay if you want that to be your final answer. There are 4 real roots, and then from here are going to come in, are going to be 2 imaginary roots. But if you would like to take this just a step further um, and find out what those imaginary roots are, we do have to go to the uh, uh, quadratic formula, at least at this stage. Eventually, you, you may learn other techniques, but for now, this is kind of our go-to. This is the one that we're going to, this is the one that we're going to use. Once again, our A is 1, B is 6, and C is 13. So as I start plugging in this information, the opposite of B, the opposite of 6 is negative 6, plus or minus 6 squared minus 4 times 1 times 13, and all over 2 times 1. And I do want to apologize for sometimes my letters aren't clear with the way my current setup. I'm often writing in my shadow, and so I have a hard time seeing what I'm doing. Not that my handwriting is the best to begin with. So this is an added challenge. So the negative 6 I'm leaving alone for the moment. 6 squared is 36 minus 4 times 13 is 52. There are 4 suits and a deck of cards with 13 cards each. So this is 36 minus 52, all over 2 times 1 is just 2. So now I have negative 6 plus or minus 36 minus 52. That is 16, I believe. Let me just double check that because I really don't want to make a mistake right now. Yes, that is 16. So that's negative 16 divided by 2. Using the techniques that I showed in the last problem, if I know that the square root of 16 is 4, and I know that since it's negative, this will become I can reach this point. If you need to go back and separate everything out one step at a time, feel free to. There is nothing wrong with doing a little bit more work to get to the correct answer when you're not perfectly familiar with everything that's going on. I'm breaking this fraction up into 2 components. And negative 6 divided by 2 is a negative 3, and plus or minus 4 divided by 2 is 2. And so then these are my other 2 roots, which is negative 3 plus 2i and negative 3 minus 2i. Again, we see that complex conjugate pairing. And so those are my other 2 roots, and if I wish to know their factors, this is, so I have to add 3 to both sides on both equations. So I have this x plus 3 equals 2i for 1, and x plus 3 equals negative 2i for the other. And for the one on the left, subtract 2i. So you get x plus 3 minus 2i. That's one factor. And then add 2i to both sides for the other. So you get x plus 3 plus 2i is your other factor. And so then your final answer would be x plus 1, x minus, x minus 1, x minus 2, and you could either write x minus 2 times x minus 2, or you could write x minus 2 squared. That is also acceptable. And then x plus 3 plus 2i times x plus 3 minus 2i. And this is the final answer. But if you can't quite go that far, that's okay. I hope this helps, and good luck.